Hello, and welcome back to Mammalian Anatomy at Keuka College. Today what we're going to do is we're going to wrap up our lecture series on Chapter 16, the Special Senses. And in this video, we're going to look at the physiology of equilibrium. So equilibrium is essentially the body's sense of balance, and so it can tell us if we're standing up straight or if we're rotating, moving forward or backwards. It can tell us how our body is balanced in three-dimensional space. And many receptors help contribute to our understanding of balance. Proprioceptors in our muscles, tendons, and joints can tell us where our body is in space and time. Photoreceptors of the eye can give us a line of sight of the horizon line, and so that can tell us if we are balanced and what our posture is. And lastly, mechanoreceptors, or hair cells, that are found in the ear. In this video, we're focusing mainly on the ear, so let's kind of talk about it a little bit more detail and kind of get into it. So the ear will actually use structures such as the utricle, saccule, and semicircular canals to detect equilibrium. And they will detect different aspects of equilibrium, such as static equilibrium. So is our head tilted or not? Linear acceleration, so being able to accelerate in a single direction. And rotational acceleration. It's also called angular acceleration. So is our body spinning in any different direction? So let's get into it and see how our anatomy of our ear can help us understand this really kind of cool physiology. So static equilibrium is essentially the positioning of our head when the head is still. So the head is not like rotating or moving around. It's just in a single position. And it can tell us whether or not the head is tilted or not. So, and to be able to identify this positioning of the head, we can use the maculae that are in the utricles and saccules. So just a little bit of a review of the structure of the macula. The utricles and saccules are going to be found in the vestibule of the inner ear. And there are going to be these specialized patches of membrane called the macula or maculae, if we're talking in plural, that are found within the utricle and saccule. So the macula has this really interesting, cool structure. It's going to have simple columnar epithelial cells at the bottom, and many of these are just going to be supporting cells, but we do have some specialized hair cells located over here. These hair cells are going to have a set of microvilli, or what are called stereocilia, coming up, and then a kinocilia, which is a true cilia over here. These cilia are going to be embedded in the otolith membrane, which essentially is a jelly-like structure that will encase these stereocilia and the kinocilia of the hair cells. Also, what is encased in the otolith membrane is the otoliths, which are essentially our ear stones. These are just some calcium. I'm forgetting. So these essentially are little crystals that are inside of our ears, and they are going to help understand both static equilibrium and linear acceleration. So we'll get into that in just a bit. Okay. So let's talk about how the utricle will contribute to our understanding of how we can identify the position or static equilibrium of the head. The macula in the utricle is going to have a horizontal organization, so it's going to be horizontally oriented. And rather than focus, just a second, rather than focusing on the words that are written here, I'd like to show you the image instead. Okay. So here we're looking at the macula of the utricle, and the macula of the utricle is going to be horizontally oriented in the utricle. And when our head is upright, what will happen is the otolith membrane will be sitting and resting directly on top of the hair cells and supporting cells. And the otoliths will be on top of that. And the hair cells will not be bending in any particular direction. However, if our head is tilted forward, what will happen is the otoliths will actually be pulled down by the force of gravity because they're rather heavy. And as they do so, they're going to tug on the otolith membrane. And the otolith membrane will slide a little bit in the direction that the head is tilted. And as it does so, it's going to actually bend the hair cells. And when it bends the hair cells, it'll activate the hair cells, and the hair cells will produce neurotransmitters that will stimulate these sensory neurons. These sensory neurons are part of the vestibular nerve. The vestibular nerve will carry this information and it will unite with the cochlear nerve to become the vestibular cochlear nerve, that cranial nerve that will go to the brain. This information that is being carried by these nerves will be processed in the cerebral cortex, cerebral cortex and the cerebellum, and it will be understood as the head being tilted. So that's how we detect static equilibrium. It is important to note that the saccule, on the other hand, has its macula oriented in the vertical orientation. And so when the head is actually upright, the otoliths are being pulled down by gravity. And then the saccule will activate the hair cells, activate the vestibular nerve, and the body will interpret this kind of activation of the macula in the saccule as the head being upright. So be aware that the utricle and saccule are going to have the same mechanisms, but because of their orientation, one being horizontal and one being vertical, it is understood as being different whether or not the head is tilted or upright, just because of that orientation. Okay. Next, I'd like to go into linear acceleration. Essentially, linear acceleration is the action of the body accelerating in a straight line without any rotation. So you've probably experienced this if you've ever ridden a roller coaster. So you're on the roller coaster and the roller coaster is just starting and it shoots you forward. And all of a sudden you get pushed back into your seat and you're accelerating really quickly forward, and you can feel that your body is moving in that forward direction. You can also feel that in a car when someone is accelerating really fast forward in the car, or even when you hit the brakes. Braking and having the speed slow down significantly is also acceleration. So if someone hits the brakes really hard, you're going to feel that linear acceleration in that direction as well. The macula of the utricle and saccule also contributes to our understanding of linear acceleration. And so let's kind of talk about how that works. Okay. I'm going to mainly focus on this diagram over here. So this is going to be the macula. When the body is moving along a single axis, when it is moving forward in a single axis, what will happen is the hair cells and the supporting cells of the macula are going to accelerate with the body at the same rate. So the body and the hair cells accelerate at the same rate. However, the otoliths are pretty heavy, and as a result, they're going to have a pretty high inertia. So it's going to be kind of difficult to get them moving from a still position. So as a result of that, these otoliths are going to accelerate at a slower rate. And so this area is accelerating quickly, and this area is accelerating a little bit more slowly. And because of that difference in acceleration in these two regions, the otolithic membrane will actually shift. And as it shifts, it's going to cause the stereocilia and the kinocilia on the hair cells to bend. And when it bends, that'll activate the hair cell, and the hair cell will produce a neurotransmitter that will activate the vestibular nerve and carry that information to the central nervous system. So, and the central nervous system will interpret that as linear acceleration. So the fact that the otoliths are heavy compared to the hair cells, and they accelerate more slowly than the hair cells, this will cause the hair cells to become activated and be able to be detected by the ear and the brain. So that is linear acceleration, only moving in a straight line, and that's it. Angular rotation or angular acceleration or rotational acceleration really is going to look at the body as the body is spinning or rotating. And I experience this a lot when I figure skate and I do my turns. I am feeling this rotational acceleration going on in my body. Or gymnasts can actually feel this too, and they're doing like flips and turns and moving in different directions. The rotational acceleration is not going to be detected by the utricle or saccule. Rather, it's going to be detected by the semicircular canals, particularly the crista ampullaris. There should be one more L here. I spelled that incorrectly. And do take a note that depending, we actually have 3 different semicircular canals, the posterior, anterior, and lateral semicircular canals. And those semicircular canals are oriented in the 3 planes of the body. And as a result, each semicircular canal will be able to detect a different type of rotation. So here we're just seeing I wanted to illustrate the semicircular canals. Here we have the anterior semicircular canal, the posterior semicircular canal, and the lateral semicircular canal. There will be a widened part of each semicircular canal called an ampulla, and within the ampulla there is going to be a special type of epithelium that will have those sensory hair receptors there. This area is called the crista ampullaris, and it is composed of supporting cells and hair cells. So we'll have the kinocilium and the stereocilium, those like hair-like extensions coming up from those cells. And those hair-like extensions are going to be embedded in the cupula right here. So the ampullary cupula. This will kind of be, again, like a jelly-like membrane and will act very similar to the otolith membrane in the macula. Again, these hair cells are going to stimulate the vestibular nerve, And so that information will be interpreted as rotational acceleration when it gets into the central nervous system. So let's kind of talk about that. I didn't write it down step by step here, but I do want to show you it as an image instead. Okay. So here we have a figure skater from our textbook. And the figure skater here is still, she hasn't moved. And so the endolymph in the semicircular canal or the semicircular ducts is still. And it's not moving. So the cupula is standing up straight. The hair cells are not activated. But as the figure skater starts to turn, what will happen is that the semicircular canal and the semicircular ducts will move along with her in the direction that she is spinning. However, the endolymph is going to be a little bit slower to start accelerating. And so what will happen is that it will have a high inertia. And instead of following the direction that the skater is spinning, it's actually going to start to flow in the opposite direction, like so. So the semicircular canal will move in this direction and the endolymph will move in this direction. And as it does so, the endolymph is going to push against the cupula and bend it over, and that will also bend the hair cells. And the hair cells will become activated. It'll stimulate the sensory neuron, and the sensory neuron will carry that information to the central nervous system, where that information will be interpreted as a rotational acceleration within that particular direction. Take a note is when the figure skater stops spinning, the semicircular canals will stop spinning along with her, but the endolymph will continue moving back in that same direction as the rotation occurs. So first it will go backwards and then it will kind of slosh and move the opposite direction, kind of following the direction that the individual was rotating. And this will actually bend the ampulla in the opposite direction and inhibiting those hair cells, and preventing them from stimulating the vestibular nerve. So that concludes our lecture on chapter 16. I hope you found it interesting and you're curious about different aspects of the special senses. If you have any questions or concerns, just email me at my Keuka College email and I'd be happy to address them. Have a great day and goodbye.